Hello everyone. Today I'll be talking about optical flow. So this is my presentation structure. Because this problem is partially covered in lecture, I'll be skipping problem formulation and energy minimization method or variational method. And the first method I will be talking about is descriptor and patch matching method. So this method formulates optical flow problems into nearest neighbor searching problems, and there are patch match, sift matching, and also there's tree searching strategies. Also, more recently, there is superglue, which learns feature matching with graph neural networks and self-attention. One of the advantage of this method is that it's quite robust to a large distance. However, it can be computationally expensive and does not compute in the entire flow map. And the second branch of method is deep learning method. Of course, there is deep learning. Um, this branch of the first CNN-based model is introduced in 2015 and is a simple encoder and decoder structure. Following that, there is SpiNet, which adopted a coarse-to-fine method, and there is PWCNets, which stand for pyramid warping and cost volume. All of them are quite important traditional optical flow methods. And also, there's a lot of recent advancements in deep learning using deep neural networks, transformers, and even more recent, what is it, data fusion, not fusing method. And advantages of deep learning method is that it has really good performance, proven to be really robust to occlusion and large displacement. However, it's quite expensive to train. It requires a lot of labeled ground truth data, which is quite hard to obtain in optical flow problems, and also it has zero interpretability, right? And there are some challenges in optical flow. The first one is occlusion. Occlusion means if a pixel is present in the first image, but it disappears in the second image. And the optical flow vector at that point is undefined. Most people nowadays use a forward and backward consistency check method. This method is proven to be really good in performance. However, they rely on an estimation model to be accurate. What I mean by this is that the key idea of forward and backward consistency check is that they first compute a forward optical flow map using a model, and then they reverse the order of the first and second image and compute a second flow map. So and then they check if they are consistent to each other. If not, is there's an occlusion. So as you can see, they rely on the estimation model to be very accurate to calculate a really accurate occlusion map. And the second approach is a variational solution. This branch of solution computes the occlusion map directly. So some of them use probabilistic approach and optimization methods such as convex optimization, energy minimization. Most of them adopted a joint method that estimates optical flow map and occlusion map jointly. Um, it is quite time efficient, however, it's suboptimal in terms of performance. And thirdly, there is motion segmentation, which is also another branch of study. And not a lot of people utilize this method, although I don't know why, but motion segmentation seems to be a whole new area to survey about. And also there is large displacement problems. As we talked about earlier, most people adopted a coarse-to-fine method. Um, there's SpiNet, PWCNet, and most recently Raft. And if we trace back, it is quite well studied using a warping theory by Thomas Brox. And also there is patch matching method. As we discussed earlier, it is robust to large displacement. However, does not compute in the entire flow. And another challenge is the dataset. The problem I see with the dataset is that it's hard to obtain the ground truth and it's not perfectly labeled. Excuse me. And there are four important datasets that most people use today. Flying chairs and MPS Intel are computer graphic generated images. They are really large and ground truths are analytically computed. However, they're computer graphic synthesized images. And if you want some real images, there's Middleberry. They contain less than 100 images, so it's quite a small data set. And they estimated the ground truth, as you can see in the second image. This troublesome the setup is for obtaining the ground truth. They have a camera moving horizontally, and they have a UV light which will show the ground truth label that is painted with fluorescent pigment. And more recently, there is Kitty. Advantages of this dataset is that it has real images, large dataset, and outdoor environment. However, it's quite expensive to obtain the ground truth as well. They are estimated with ensemble of high quality sensors. So the problem is that can we really trust the ground truth? What if it is wrong by 1 or 2 pixels? Will the result, can we accept it? Well, one solution to it is unsupervised learning. So we don't need the ground truth anymore. The key idea is that you feed first and second images into a encoder and decoder based or whatever model you have, and then you reverse the order and compute another backward flow, and then you construct a loss function that check if the first flow is a negation of the second flow. And it is good because it does not rely on ground truth, which is really hard to obtain. However, it does not perform as well as supervised learning methods. And after doing a small survey, here are my reflections. Is optical flow a good PhD thesis? Well, it is a good, well-formulated problem, but as I can see right now, it's quite competitive and probably will be expensive to study in the future. Um, Speaking of how I can make contributions, of course I can invent an algorithm that outperforms all sort of algorithms, but I don't think that's practical, like, especially I just stepped into this field. So maybe even easier, can I make a dataset that reviews a problem? So for example, I want to know if SOTA algorithms can handle reflections. I can make a dataset like this, mirror balls. This is my computer graphic assignment. I think it's quite interesting if I generate thousands, tens of thousand images like this and benchmark against SOTA algorithms and see if they still compute a correct optical flow. And that's it for my today's like presentation. Thank you.